All right, howdy y'all. So we're going to be attacking 817 first. So we're going to start off by remembering a few definitions. So C naught is the set of functions who vanish at infinity. And what that means is that if I take some epsilon, the values of the function that are greater than epsilon are bounded in, the x values of the function that map to that is a bounded set. C infinity C is the set of functions with in C infinity with compact support. And again, C infinity is the set of functions that are in all Cn, where Cn is the set of functions whose nth derivative is both exists and is continuous. And then lastly, we have S, which is F, the functions in C infinity such that this guy is less than infinity for all n in alpha. And we define this thing here by the supremum across all x in Rn time of 1 plus the magnitude of x to the n times the alpha derivative of f of x. Okay? So real quick, we get that C infinity C is a subset of S, obviously, because if it is continuous with respect to all of it, if all of its derivatives are continuous, so this guy is continuous and it has a compact support, and outside of the support it has to be 0, but that's bounded, which means that the function must be bounded, which means that this guy is bounded, and x as it, so for any given x, this whole thing will be finite. And then, which is exactly what it means to be in here. So we get that this set inclusion holds. So we're going to break this up into two videos. So our claim is that C infinity C, and hence also S, is dense in LP for P finite and greater than, sorry, that should be between 1 and infinity, right? Yeah. Yeah, between one, yeah, right. I was like, I don't think we ever worked with anything less than 1. So, and in C naught, okay? So the first part we're going to focus on in this video is going to be this one. Then we're going to take on the C naught second case. It's basically the same proof, so I'm just going to turn off the video and replace some things. So here's how it goes. We're going to start with F and LP. Then there exists an epsilon, and epsilon greater than 0, such that there exists a G in CC with the difference of them in the p norm being less than epsilon over 2. We know that such a function exists because of proposition 7(9), which tells us that if we have a rate, we're working with the Lebesgue measure. So because this is the Lebesgue measure is a radon measure, we get that CC is dense within LP. Right? Because we're in Rn, so we're working with the nth dimensional Lebesgue measure, which we know is radon. So this directly gives us the density there. So we really only need to find this one because we can do it using transitivity of density. So we let B be an element of C infinity C, such that it has its integral is 1. Now, what we get from this is we know that this exists because of the discussion during 8.1 where they show that this set is not empty, and then and then we just make it so that it has L1 norm 1, right? So then we take, so then we have two theorems that we're going to use, the ones that we proved before, 8.6d, which tells us that the convolution of two functions with compact support is the support of the convolution of two functions is a subset of the Minkowski sum of the closure of the Minkowski sum of the supports of the functions. Since both of these guys have compact support, Minkowski sum of them has compact support, which means it's equal to the closure. And then we get that this guy is also having compact support. Then, for the second one, this tells us, 8.10 tells us that the convolution of two functions is at least as smooth as the smoother of the two functions. And since B lives in C infinity, this guy also lives in C infinity. So it lives in C infinity C. And then we also get that the norm of this guy, the p norm of the convolution is less than epsilon over 2 for small enough t. And this is from 814, where we showed that as t goes to 0, this guy is going to be less than the product of this integral times that guy. And since this is 1, we get that the norm has to be going to epsilon over 2. So then this gives us density in LP, because we show density in CC, which is dense in LP by theorem 7.9. So this gives us the first one. In the next video, we're going to go over why it's also true for C0.